What we're going to jump into now is really some of the focus on the key event relationships, and more importantly than the key event relationships, really how we assemble the evidence to support AOPs, or that's going to be the main topic this afternoon. So again, this morning, gave you a bit of an introduction to what AOPs are and hopefully why we're interested. We discussed the 5 principles of AOP development, so hopefully you're all familiar with those now. Talked about some of the best practices for key event identification, and then you guys had the hands-on exercise to try and give that some hands-on experience. And then finally, the tour of the AOP knowledge base. So now we want to take a more detailed look at the kind of information we assembled to support the key event relationships and the kind of information that goes on the key event relationship pages of an AOP description, and then how that leads into the weight of evidence evaluation.
Okay, so my presentation is going to be extremely short for multiple reasons. One, it is short to begin with, and second, I'm late starting, right? So last time I talked to you from the perspective of someone who is a user and developer of all these rules that have been developed. I talked about how do you go about designating and naming the key events. And that's kind of what the first exercise revolved around. Now I'm just going to briefly talk about how do you go about key event relationships. And it's really important to remember that key event relationships really matter. This is kind of where most of the weight of evidence gets conducted. It's on these key Rs and not necessarily on the key events. And then Dane is going to go into quite a bit of depth on weight of evidence evaluation, and he's going to address some of the questions you raised about causality versus the correlation and so on. So the first thing is you need to name the key event relationship, and that's actually very easy to do because pretty much the syntax for naming is... So basically, the wiki forces you to name the key event relationships correctly in so many words. The way that the name is made is you have to describe the relationship, and you have to basically say this leads to that. Key event 1 leads to key event 2, and that is basically the name of your key event relationship. There's just a little bit more to it, and that is that you actually have to designate whether key event 1 leads to key event 2 directly or indirectly. And when I started doing this work, it was a little bit confusing to me as a user, to understand what is meant by direct and indirect and why are these designations there. Initially, when I started thinking about it, I was kind of thinking about it as a biologist, some indirect, direct effect, and so on. Turns out the main reason for indicating whether something is direct, meaning something that connects two adjacent key events, or indirect, meaning something that connects key events that are not adjacent. The main reasoning behind it is actually to facilitate better weight of evidence assembly. So really what I mean here is, and those of you who were in my group when we were developing the AOP, what we quickly agreed on is that we should outline the biology. What is biological plausible? How does this system work based on the knowledge we have? And that is really your long AOP here. But sometimes, as you start looking at the biological process you outline, you realize that many of these key events are not really well elucidated, are unknown, or are not measurable, right? So in that case, what you can do is you can start designating these indirect key event relationships, which are then going to facilitate better weight of evidence evaluation because you actually might have information for these kinds of key events. So you're kind of bypassing some of the biology in the second step when you start conducting the weight of evidence evaluation. So here's an example of that. And those of you who are toxicologists and biologists have probably seen many papers in toxicology demonstrating that acetylcholine esterase inhibition leads to the mortality. It's very easy to find a bunch of papers showing that a variety of chemicals can do this. So this relationship is portrayed here using this indirect KR designation. The reality is there's more to this relationship. If you read biology literature, what you're going to find is that actually there's a series of steps by which this process is mediated and happens. But once you engage in the tox literature, what you're going to find is there's not much out there that addresses those 3 steps. Nevertheless, the amount of evidence that links these two these 2 key events is really overwhelming, so you can really go ahead and actually start using that for the weight of evidence. So this is one of the examples. There are many examples of this. This is another one. And this is the one actually that I'm sure aromatase group discussed a little bit, and so did we in the back. You know, what do? Do you put all of these boxes in? So in this case, you know that plasma reduction of circulating E2 leads to reduced vitellogenin production in the liver and hepatocytes. And then that leads to reduced circulating vitellogenin. The question is, you know, how much data is out there on whether chemicals actually reduce the VTG production in the hepatocytes? And the answer to that is not that many. That is not typically something we measure. So again, you're designating this indirect key event relationship to facilitate better weight of evidence evaluation. So again, you start by, you know, developing something that's biologically plausible, but then in this second layer, you may kind of trim it down, and this is, in a sense, one way of trimming it down without trimming it down. So why not just take this key event out, right? You may ask. And the answer for that is that you want to maintain the modularity. You want to keep these key events, because intermediate key events in play, because they may be very important for interaction with some other AOP, and they may represent important part of the network itself. So that's why we don't just necessarily cut them out, and maybe eventually you would weed them out, but not at the initial stage. Okay. Another thing you should do is you should name it, but you should also describe the key event relationship. And the important thing to remember, and I kind of touched on this before when I talked about key events, this is an opportunity to actually become specific, right? So this is where you can actually convey some specificity. And in this case, you can add the context of the tissue. That's, for example, what is shown here. But there are additional cases, and this is a good one. And I've shown you this already. I'm going to repeat this because now you're going to probably understand this a little bit better than the first time I showed it. But basically, when function is equivalent, right? So function here is equivalent regardless of these context variables, but outcome is dependent on these. So these outcomes are now dependent on these context variables. Then you can use the key event relationships rather than key E to provide the specificity. So that's what key ER is there for. And this is just the final example I'm going to talk about. So this is really going back to the acetylcholine inhibition that I mentioned to you before. And what you see here is here's that indirect key event relationship, but here's actually the whole network of events that results in that adverse outcome. And what you can quickly see is that acetylcholine accumulation in the synapse, which is the key event 1, can have different phenotypic consequences, right? Depending on the biological context. So one biological context is in cardiac tissue, and the other one is at neuromuscular junctions. So what you see is you're initiating 2 distinct mechanisms by which you're going to converge on the common key event and adverse outcome. And key ERs are very helpful in delineating those differences and outlining the biology and demonstrating the biological plausibility. Okay, so I think that's all I had.
So, Dalma just introduced you to the concept of direct versus indirect key event relationships. And again, one of the key goals there is to really be able to map in these key events. In the acetylcholinesterase example she showed, where we had this series of intermediate key events. They're things that could be measured, but they're not routinely measured. They're things we know based on the biology, the basic biology. This is the way this system functions. We've got this massive amount of correlation evidence between acetylcholinesterase inhibition and adverse outcome of mortality. If we add to that this plausibility for how that happens, now we've strengthened the overall weight of evidence. we just have correlation, sometimes people are like, well, I don't really know if that's causative. But if you can map out this series of key events that show, yeah, this is completely consistent with our understanding of normal biology, strengthens your evidence. So that's why we want to build in those indirect key event relationships. We can take into account that massive weight of evidence, even if it doesn't match each of those pairs of key events that are in our chain. So direct and indirect, again, talked about the use of the key event relationship descriptions to try and add specificity while maintaining our key events as general as possible so that we can link them in this modular aspect to other AOPs so that we can build these networks. So what I want to get into in this section is really introduce the different types of evidence that we use to support the key event relationships. Because on the key event relationship pages of an AOP description, this is the bulk of the information that's going to be there. And this is really the scientific underpinnings for extrapolating along the AOP. I mean, this is what it comes down to, really, is this biological evidence that we have. So there's two main types of evidence that we include on the key event relationship pages. One of those is plausibility, and the second is empirical support. So first of all, what do we mean by plausibility? Here we're just talking about what is the structural or functional relationship between those two key events. What's the mechanistic basis for believing that the key event upstream should influence the key event downstream? And this is typically based on our understanding of the normal biology. Most plausibility is just based on basic biology. So as an example, if we have an enzyme that catalyzes a reaction, cyclooxygenases catalyze the conversion of arachidonic acid to prostaglandins. That's the basic biology. Our inference based on that, if we perturb that biology, if we inhibit that enzyme activity, we can pretty readily infer from that if you inhibit COX activity, you'll reduce the conversion of arachidonic acid to prostaglandins. Prostaglandin concentrations will go down. Another example, we have receptor activation triggering, say, messenger RNA synthesis, protein synthesis. Take the example of estrogens. Estrogen binding to the estrogen receptor induces the production of the egg yolk precursor protein vitellogenin. That's the basic biology. It's been outlined. Based on that, we can infer that if we were to perturb that biology by exposing an organism to an estrogen receptor antagonist, it would make sense that we could get a reduction in vitellogenin production. Fairly straightforward. Relating to the DNA alkylation case study, again, basic normal biology. We have DNA repair mechanisms that are able to repair and remove alkylated DNA, preventing mutation. DNA is replicated. If we impair or overwhelm those repair processes, it's completely plausible that we'll accumulate mutations and that through DNA replication, those mutations will be propagated and you'll increase mutation frequency. Again, that's an argument that's based on lots of scientific understanding of basic biology, of DNA replication, DNA repair, simple processes. Finally, we'll take the example we had earlier, dating back to Silent Spring and thickness of eggshells. I mean, it's pretty apparent that thick eggshells reduce the vulnerability to physical damage. If we thin the eggshells, it seems pretty plausible that you could make those eggs more subject to damage, right? These are the kinds of things that we're talking about in terms of biological plausibility. A lot of it, a lot of AOPs can start out as nothing more than, this is what I understand about the biology. This is what I think would happen if I actually broke this part of the biology, if I perturb this system, if I impair this process. This is what I could hypothesize should happen. Having that basic biological understanding really gives us an explanation for why we're seeing what we're seeing, which is incredibly compelling when it comes to weight of evidence for supporting a prediction. So it's an important part of evidence. But we'd also like to back it up with empirical support. We'd like to say, this is what I think would happen if I perturb the normal biology. Now let's see some data where I actually do that, and do I see those consequences or not? That's what we're really talking about with empirical support. Specifically as it relates to the key event relationships, we're looking at studies that demonstrate that when the upstream key event is impacted, downstream key event is also affected. We can use empirical support to establish a relationship between an upstream key event and a downstream key event, even if we have no idea what the structural functional relationship is. It can be strictly correlation-based evidence. I saw this, and I also saw that. You can do that. In general, if you have strongly established plausibility, a fairly small amount of empirical support will give you strong confidence in your description. You're saying, here's what I know based on the biology, and I've tested this, and it's completely consistent with what I expected. So you can be fairly confident you got a good description. If your plausibility is weak, you don't really understand what the relationship is between, say, acetylcholinesterase inhibition and death. There's an association there, but you have no idea how it happens. Then it takes a lot of empirical data to convince yourself or to convince a regulator that they can make this measurement and predict that outcome if they don't really know what the causal relationship is. As it comes to empirical support, again, the strongest support are those support that establishes causality. So if we have a correlation, we know that correlation is not causation. We could come up with some incorrect associations based on simple correlation. So, there's classic examples, like we might conclude that cold temperatures cause the influenza because when it gets cold, people congregate indoors and virus transfers easier and influenza is propagated. So really the cause of influenza is the virus, not the temperatures, but there's an association there. So again, establishing a causal relationship between the key events really provides us greater predictive confidence. So a lot of what we're trying to do in evaluating the empirical support for AOPs is trying to think about how well that empirical support supports the idea of causality between those two key events. And so in considering that, again, we've adapted the Bradford-Hill criteria, which were basically established back in the 1960s, as a way to assess causality in epidemiology studies. And there's, I think, 9 different criteria or something. Over the years in the human health mode of action framework, they've kind of winnowed those down into a fewer sets and considerations. For AOPs, maybe a little bit more. But it's basically fairly logical stuff. It's basically saying, if A causes B, the following should be true. So the severity of a stressor needed to evoke some change in A should be less than or equal to that needed to evoke the change in B, if A causes B. Okay? A should always precede B. Can't really be the cause if it happens after B had already occurred. The change in A should be observed with greater frequency than the change in B. And that, again, relates back to those concepts we talked about earlier of essentiality of the key events, but that the key event is not necessarily sufficient. So just because we have some change in A doesn't mean it's necessarily going to cause B unless it has sufficient amount of change. Okay? So as it pertains to toxicology then, we can think about this in terms of dose response, temporal, and incidence concordance. Okay? Dose response concordance basically saying the dose or concentration that's needed to evoke some change in the upstream key event is less than or equal to that produces a change in the downstream key event. Temporal concordance. We should see effects on that upstream key event before we see changes in the downstream key event in a temporal sequence. And then incidence is really talking about occurrence in a population, for example. So if we expose a population of organisms, we're looking at, do we see some observable change in their histology? Do we see tumor formation, for example? the upstream key events earlier in that progression toward tumor formation, we should see those with greater frequency in the population than we see that final outcome. Because again, even though we've impacted that key event, it might not be sufficient to drive it all the way to the end in an individual. Oh, and as was brought up earlier, the critical assumption in all this is that we can actually measure these different events with the same precision and statistical power. So, we may violate this assumption of dose-response concordance simply because we can't measure it as sensitively. It looks like we don't have dose-response concordance because we can measure the downstream key event with 10 times the sensitivity that we can actually measure the upstream event. So that has to be factored into the equation. So to just illustrate this graphically, again, in assessing dose-response concordance, the basic question is, does the key event upstream occur at lower doses for the tested stressors than the key event downstream? This is the kind of relationship we would want that would support concordance. So key event 1 is occurring at lower concentrations than key event 2. This would be a scenario where you don't have support for dose-response concordance. Key event 2 occurring at lower concentrations than key event 1. Seems fairly straightforward, right? What dose-response concordance is not, and this causes a lot of confusion for toxicologists, particularly as we started doing AOP development, started doing weight of evidence evaluations. If you go into the wiki today, I'm sure you can see examples of where people are arguing support for dose-response concordance basically on the basis that my key event is dose-dependent. So if I expose the organism to different concentrations of the chemical and I'm measuring vitellogenin, I see a dose-dependent response in vitellogenin. That's not dose-response concordance. Concordance would say the impacts on plasma estradiol are occurring at lower concentrations than I see the impacts on plasma vitellogenin. This is an example of real data addressing this issue of dose-response concordance. So here we have 2 key events from the DNA alkylation example. Key event 1, looking at the formation of the DNA adducts. And you can see here we have significant effects down to 100 microgram per liter. Effects at all higher concentrations. Key event 2, we're looking at a cell proliferation response. We don't see those effects until we get to higher doses. So this would be an example where the data support dose-response concordance, would be consistent with a potential causative relationship between those key events. Temporal concordance. Does the key event upstream occur before we see effects on the key event downstream? Again, same type of plot, only here we have time on the x-axis rather than concentration. Principle is the same. For key event 1, we start to see changes in that biological response before we see changes in key event 2. So in time, that one occurs first. This would be a case that violates that assumption. Here we have significant changes in key event 2 before we start to see anything in key event 1. Again, this is assuming we can measure them both with similar precision and on similar time scales and so on. This is an example from a case study from group 1 that was working on the aromatase example. These are real data generated in the lab pertaining to key events 1, 2, and 3 in this pathway. So basically showing the effect on estradiol synthesis in the ovary. You can see impacts on that within 6 hours. We don't actually see impacts on circulating concentrations in the plasma until 12 hours. No impacts on vitellogenin until 24 hours. So again, entirely consistent with temporal sequence of those events. Same as with dose-response concordance, temporal concordance is not just the time dependence of a single key event. It's always one key event compared to the other. How do they fall in a sequence? Final example, just talking about incidence concordance. So again, this is a case where Our y-axis is the number of individuals in a population that are responding to the treatment. So we have different doses here. What you see is for these 3 key events in the sequence, no matter what dose we're looking at, key event 1 is always occurring at a greater frequency or incidence in the population than key event 2, which in turn is occurring at greater incidence than key event 3. More of the population is responding. So those are the first 2 things that we want to build into our weight of evidence descriptions for the key event relationships: plausibility, empirical support. A special component of the empirical support, it's really not different from the empirical support, but it's maybe a special kind of empirical support, is quantitative understanding. How well can we quantitatively infer how much change in key event downstream we're going to get if we have some unit of change in the upstream key event? And what does that relationship look like? So these quantitative relationships are really defined largely on the basis of response-response relationships. So here's your change in key event 1, change in key event 2. Might be a strictly linear relationship. So as key event 1 goes up, key event 2 goes up. Maybe something like a sigmoidal type shape. Could be a threshold where you have to get a certain amount of change in key event 1 to actually see a quick burst of change in key event 2. These can take lots of different shapes, but that's the idea. We want to define what that function looks like. There are many cases in which, depending on the underlying biology, things like feedback loops, adaptive and compensatory responses, that underlying biology may not describe itself simply as some regression function or simple equation. In those cases, we may need to use a more complex computational model of the biology and potential modulating factors to actually get good predictions of what to expect from the downstream key event. This includes, again, both factors involved in the biology, but also external modulating factors that we know to influence those relationships. So, we talked about the example of feedback regulation, but things like temperature dependence or interaction with other pathways, those can all maybe modulate these response-response relationships. So the more we understand about those modulating factors and the better we can model and predict them, the better we'll be able to predict the outcomes. This is just an example, again, from our own research related to the aromatase inhibition AOP. And what we see in the data here, these are 2 key events in this pathway. So estradiol synthesis in the granulosa cells of the ovary and the actual circulating concentrations of estradiol. What we see when we expose to an aromatase inhibitor is within 24 hours, we see a reduction in estradiol production. But if you continue the exposure at a set dose, what you see over time is that effect getting less and less, such that by about 8 days, there's actually no significant difference from the control. Those organisms are producing estradiol at the same rate as the controls. What we see as an explanation for that is that they've actually increased the transcription of aromatase itself, increased the transcription of follicle-stimulating hormone, which helps support the production of estradiol. So basically, the organism has triggered a feedback response and tried to compensate for that stressor. And so this is not this simple linear function or sigmoidal function. It doesn't explain itself that easily. And so to accurately predict these kind of behaviors, we actually have to build a more sophisticated model. And so that's essentially what we did. We built a model of the hypothalamic pituitary gonadal axis, some of the key feedback processes involved, maybe the time delays that are involved in those, and basically produced a model that could reproduce those effects, the direct effect of the chemical, the compensation response when you actually remove the stressor, those sorts of things. So those are the types of things we're talking about in terms of quantitative understanding of the key event relationships. Again, since in many cases we may have to build sort of models, predictive models that can model these behaviors in order to produce these, we just had a workshop, a month ago, a little over a month ago, where we talked about building predictive models around these AOPs and the key events in the AOPs and how to help facilitate that in how we capture information in the AOP descriptions. And so these next couple recommendations really came out of that workshop. So the modelers that were there really said, one of the things that would be really useful for us for building these models is if you could provide some indication of the temporal scale over which the upstream key event influences the downstream. Is this stuff occurring in a matter of seconds? I see a change in estradiol concentration. Should I expect to see a change in vitellogenin in seconds, minutes, hours, days, weeks? Having that kind of temporal context could help with the modeling. Also, we want to include other information that could be useful for deriving this response-response relationship. So if we identify data sets that could be used to derive these response-response relationships, that's really useful information. Potential sources of parameter information for building these biologically based models. So as you're going through, you're finding information about estradiol concentrations, and you come across, something like a reaction rate for enzymes, Vmax, KD, all these kind of dissociation constants and things like that. If you have sources of those, maybe make note of that in the quantitative understanding description in the knowledge base. When we describe key events in the AOP, key events are generally written to be as generalizable as possible because we're trying to link them to multiple AOPs in the knowledge base. When it comes to key event relationships, because we're providing specific evidence that supports that particular relationship between these two key events, and we want to be able to evaluate that evidence, here we actually want to include specific details about what studies it was derived from, what species were tested, the conditions, the doses that the relationship was examined at. Put that information in there because all that's important for assessing the weight of evidence, assessing how broadly the base of support is. Is all the evidence from a single species, but we're saying the taxonomic relevance of the overall AOP maybe applies to all vertebrates, but it's only been tested in one fish species. If we can capture that information there, we can see, okay, this one was tested in one species, this other AOP, we've got support from 15 different species. That helps with the weight of evidence evaluation. So key event pages, or the key event relationship pages rather, overall, collectively, all this information that we're assembling on the key event relationship page is intended to provide the foundation to assess the overall confidence and certainty in that particular relationship. And as we assemble that for each of those KERs in the AOP, both supporting evidence for direct and indirect relationships, we basically provide the foundation to understand the confidence in extrapolating the entire length of that AOP. So that's really where we're trying to move. So next we're going to jump back into the topic of weight of evidence evaluation. So again, the exercise we just did, we wanted to get you thinking about the types of different evidence that we had. And so far, we've focused really in the previous section of the lecture here, focused on assembling the evidence that supports the individual key event relationships. So we've talked about temporal concordance, dose-response concordance, primarily referring to key event upstream, key event downstream. So just a single pair of key events. And that's really how we organize that evidence within the knowledge base. But again, as we lay out that series of key events for our given AOP, what we'd like to do in the final weight of evidence evaluation is look over that whole spectrum. So what we're going to do in this section is talk a bit about how we can organize information to support that overall weight of evidence evaluation for the entire AOP, not just each individual key event relationship. and discuss some of the challenges related to that. And that directly gets back to this question of how we design our experiments and produce the kind of data that would support an AOP. So in describing the key event relationships, again, much of the evidence is put on assembling this weight of evidence. In the knowledge base, this is typically captured as bulleted text. Okay? This is a living document. There's new studies being generated. So we're providing kind of these snapshot synopses of, this paper provided evidence of this. This paper provided some evidence of this. Cite the reference, maybe give a little background about the species and the conditions under which that was tested. So now when you try to assemble that for the whole AOP, you've got maybe 8 key events. So you got something like, 7 key event relationships? Or is it 9? I don't know. Anyway, 7 or 9 key event relationships. And you're trying to compare across all those to assess dose response and temporal concordance. Now, doing that from a set of bullet points, flipping back and forth between different key event relationship pages, not so simple to do. What we're really interested in here is evaluating the pattern of response in terms of dose response, temporal concordance, across those different key events. And so one of the ways that we can do that is try to organize all that information that's captured on those key event relationship pages into tables that help us effectively look at those patterns across that entire AOP. Okay? So that's what we call concordance tables. They're basically built to help us evaluate those data. This is an example of what a concordance table might look like. So here we have our time scale going along the horizontal axis. You line up your key events in sequence. So again, if things are as we think, if they're causally related, key event 1 should precede key event 2, which should precede key event 3. So you put them in time series order. We put our dose concentrations of our stressor on the vertical axis, so 3 different doses, and then we start to organize the information. And in this case, we're looking at the severity of the response, so just an overall grade in how severe the response was in those different key events. So this might be estrogen production in the ovary, vitellogenin production, oocyte maturation, something like that. Okay? So we're just evaluating the severity. So what you can do with this table pretty quickly is if you look, we'll just pick this dose. We'll take this one dose, we look across time, what do we see? We see pretty severe effects here, less severe at our 3rd key event. Is that consistent with temporal concordance? Pretty consistent, right? How about at the high dose? Same thing. Pretty severe effects on our first 2 key events, somewhat less severe at the 3rd key event. That's kind of what we would expect to see. If we look at any one of those key events across doses, what are we seeing? We're seeing an increasing severity with increasing dose. It's what we expect to see within a given key event. When we look across the doses, less severe effects at equivalent doses on key event 3. Okay? So organizing the information in this manner allows you to pretty quickly across all your key events assess whether you've got concordance or not among your AOP. This is just another example. Here we've got 4 different key events. It's kind of showing the time points at which they're occurring. You've got your doses, again, going on the vertical axis here. And again, if we look at each key event, you see as you increase dose, you're increasing the proportion of the population that's responding to that given treatment. So you've got incidence concordance as you move across the different dose ranges. You look across your AOP, your different key events. You see at the lowest dose, you're seeing effects on key event 1, but you're not seeing anything on the other ones. You go to a higher dose, now you're seeing effects on key events 1 and 2, still no effects here. Higher dose, you're starting to see some impacts here, but less frequently. So those are examples of data that would support dose response, temporal, incidence concordance, okay? And just a note here that the lack of effects on a downstream key event, even though you've seen something upstream, is not an indication that your AOP is not valid. It's just simply the expected pattern according to this temporal concordance. So you've got to push the system fairly hard to get it to go all the way to the final failure. Again, the idea is that each key event is essential but not necessarily sufficient. Just because we cause a change in that first key event doesn't mean all the dominoes are going to fall. We have to hit that event hard enough to make the rest of the dominoes fall. Okay? So these are rather ideal concordance tables. You'll never see one like that, I can guarantee it. Nonetheless, these were found to be particularly useful for the mode of action evaluations that were conducted for human health risk assessments. That group that's been involved in the weight of evidence evaluation for that purpose has really stressed the importance and the utility of making these concordance tables as a way to help aid the weight of evidence evaluation. But we note here that human health mode of action analysis is based on a single chemical. Okay? It's very chemical focused. Application to AOPs can be a bit more challenging because, again, we're not describing chemical-specific pathways here. We're actually taking in evidence and thinking about this from a multiple chemical perspective. And so in AOPs, we'll often be considering evidence from studies with multiple different chemicals that are impacting the same initiating event. In some cases, where we have key event relationships that are actually shared among different AOPs, you may have evidence for those key event relationships that support that individual key event relationship that actually comes from studies done with chemicals that are acting on different molecular initiating events. So the examples earlier, so impacts on vitellogenin synthesis and subsequent connection to oocyte maturation, for example, we could be looking at that as a result of an aromatase inhibition pathway, as a result of an AR antagonism pathway, as a result of an ER antagonism pathway. So we can have evidence coming from lots of different sources here. So that makes the building of these concordance tables a little more challenging because we can't necessarily directly compare doses if we're using different chemicals with vastly different potency. Can't put them all in one table and compare them. Time course can vary with chemical, again, based on the different potencies of the chemical, different toxicokinetics. Similar issues apply when we're using data from multiple species. So we can't necessarily look at the temporal concordance if we're mixing trout with zebrafish. Totally different developmental stages and so on. So the practice so far in trying to adapt these concordance tables for AOP has been to basically build separate concordance tables for each of these different chemical sort of species combinations separately. You may incorporate it all into one table, but you have to kind of break them out into these groups in order to evaluate concordance. So this is an example of what a concordance table might look like for an AOP, where we've got one species here exposed to chemical A over 3 different concentrations. We'd look at the concordance across our key events to the extent that they've each been measured. Those measurements may be from different studies. Then we've got another experiment exposed to a different chemical. There's a different dose range, so we can't really compare A and B. Here's B tested, again, in another species altogether. So we kind of have to deal with each of these separately, but we organize it into a table, make the evaluations, and then try to do the overall assessment. Challenges associated with this. This was brought up one of the earlier questions today. But often what we're comparing is the quote-unquote dog's breakfast of studies. People aren't really designing experiments, at least currently, for the express purpose of supporting AOPs. They're not designing the studies to look at incidence or temporal concordance or whatever. And so what you end up with when you're building these concordance tables is you got experiments with different routes of exposure, different dose selection, your endpoints are maybe different. You've looked at 2 key events in this study, and you've looked at the different 3 key events in that study, and you're trying to put them all together in this table and see if it all hangs together or not. It's not so easy. So get the idea there. So we can take some steps to try and normalize for some of these differences. So one of the big ones is dose selection in studies. That's one that we can sort of deal with to some extent. One of the recommendations there is to try and use benchmark doses and move away from just simple low X and no X, which take basically the doses you've selected and say at which dose do I see a statistically significant response. So there, your determination of the effect level is directly dependent on the doses you selected to begin with. And this is just an example here where 2 different experiments, basically conduct 2 different experiments. We identify a lowest observed effect concentration. Okay, in this experiment, you can see it down here, this experiment up here, and that's just based on the statistics. But if we actually fit a regression line to that dose-response relationship and calculated something like an EC50 or an EC10, what you see is those 2 experiments actually gave you the exact same answer. You'd have the same benchmark dose. It's just essentially the same response. But because of the difference in design, if you based it on a low EC, you might have a difference of 10-fold between those 2 experiments simply based on the dose selection, even though the potency was exactly the same. So ideally, you'd like to use benchmark doses whenever you can, but of course, this requires testing at multiple doses so you can actually fit a regression to it. If you're only doing 2 doses or 3 doses, it's pretty hard to do. So again, that's an ideal situation, but we can't always do that. So if you can't use benchmark dose, one of the things you can do and probably should do is actually incorporate information on the dose spacing into the table so that you summarize that information and you can look across your key events and say, okay, I don't quite have dose-response concordance here, but I didn't actually test the concentrations low enough in this study that looked at this key event to actually evaluate. It's causing the effect at the lowest dose I tested, and probably had I gone lower, I could have shown that that upstream key event was actually occurring at that even lower concentration, but I didn't look at it in this study. But if you have that information in the table, you can better assess that kind of situation. Another challenge that we can encounter are things like transient responses. So, again, I talked earlier about this pattern of effects that we saw where we see the impact at 24 hours, but the organism starts to compensate. If you looked at 8 days, you'd have said there's no effect on key event 1. When actually there was an effect, you just didn't look early enough in the time course to see it. So, again, you have to kind of take these things into account when you're evaluating the data. You might have missed some things. You may not be able to. Another issue with the temporal concordance is that something like a reproductive effect, you can't even measure it on a time scale finer than 7 days. You've got to have, say, 7 days of egg production to even see if you're impacting it. So your other key events are on time scales of hours, maybe a day. You've got to have 7 days to even make the measurement on the reproductive endpoint. So, your ability to assess whether it occurred at an earlier time point, you have no idea. You can't measure it that early. Those are just basic limitations. Again, the focus on all this is to evaluate the pattern across the different key event relationships, not the dose or time dependence of the individual key events. No one table format is going to cover all cases, so as you see your particular dog's breakfast of studies that you have to deal with, you have to kind of tailor your table to provide you the best sort of summary and evaluation you can. Where possible, you want to normalize for some of those issues like dose spacing or different routes of exposure, things like that, where you can. You're not always going to be able to do that. But overall, again, these tables are pretty helpful for identifying inconsistencies in the empirical support across taxa, different species, different stressors. You can pretty quickly see the data that don't align with the expected responses. But again, there's a lot of assumptions in that. You almost never have the ideal sort of data sets. And so those inconsistencies are often explained by differences in the study design and implementation. So the more you understand about how those studies were conducted and what the reasons for the differences are, the better you can evaluate whether those data actually support or reject your AOP. Concordance tables work best when you have a large body of data across the key events for individual chemicals in the same or closely related species, and or you can normalize effectively across all these different studies. And again, the whole point of that previous exercise is that this is really aided if we can design studies for the express purpose of establishing weight of evidence for AOPs. The more we can think about that going in, the better we can design these studies for this kind of an evaluation. So I think by now you got the message. Data upon which we base this is generally not the ideal sort of data sets. As a result, it's going to require expert knowledge of the studies that are going into this evaluation to really do a careful evaluation, see whether it really all hangs together or not. And in most cases, the AOP user, somebody going into the knowledge base, seeing all this evidence that you've laid out in these bullets and so on, isn't necessarily going to have anywhere near the background knowledge about these studies to make that evaluation. And so that's part of the reason that part of the practice of AOP development is to actually do this weight of evidence evaluation and provide calls, sort of your opinion about how strong that evidence is, so that somebody else going in there who doesn't have all this background information can get a sense of what the overall confidence is, where the weak points are in the AOP, what it might be useful for, and then if they want the details, they can dive into all the background information that's there presented in a transparent manner. But if they want sort of the first cut, give you your best guess, that's there for them to reference. So let's move on then to how we actually make these weight of evidence calls. So again, we discussed how we'd organize the information to support that overall call. Now I'd like to talk a little bit about why we want to make these calls. We mentioned that briefly already. Discuss rank ordering of the different evidence types, which evidence we think are more compelling than others. And then introduce some of the guiding questions that are being used to inform the weight of evidence calls, what we assign as strong, moderate, or weak when we fill out those tables in the knowledge base. So first of all, why do we care about doing the weight of evidence evaluation and making these calls? Because basically, fit for purpose for different regulatory applications is going to be based on the level of confidence that we have in the AOP. So as we mentioned earlier, there's lots of different potential regulatory applications, risk assessment type applications. So you may have things like screening and prioritization, where you've got a bunch of chemicals and you want to say, which of these should I actually conduct an avian reproduction assay on? Which of these might cause embryo larval lethality in fish? Where do I want to put my resources? Or how can I develop a hypothesis about that chemical that might help me direct my testing on this? Okay? So that's going to be followed up with additional testing. If I get it wrong, the consequences aren't too horrible. So I can tolerate greater uncertainty in that prediction. I might just base it on an AOP that's little more than a hypothesis. It's better than nothing in terms of directing my efforts. If I want to get into quantitative risk assessment, I want to say under this particular exposure scenario, what's the actual probability that I'm going to see this adverse outcome? I may want this to be much more precise. And if it's a high tier, sort of high impact risk assessment, I better be pretty darn certain what my outcome is going to be. before I'm going to be confident using that AOP. As we talked about earlier, to reduce that uncertainty in a predicted outcome that's based on AOP, maybe derived from in vitro data or whatever, you're going to need lots of data. That's going to cost time, effort, so on, to develop something that gives you kind of this high level of certainty. And so understanding where you're at sort of along that spectrum informs what kinds of applications that AOP might be suitable for. So as we mentioned earlier, AOP users may not have expert knowledge required to really assess the weight of evidence. So it's helpful if the developers provide some calls. This is still a subjective determination. What I think is really strong support for my AOP, somebody else might think is pretty weak. I might say, I did these really 5 really great experiments, and they provide bang up support for this. Somebody might come back and say, well, you only tested 1 chemical in 1 species. That's not very compelling support in my mind. So it's fundamentally subjective. And so basically what we want to do is provide a call. We want to back up that call with a rationale and basically provide a synthesis of the data, a summation, and again, transparency. All the data, all the support is there for you to look at, for you to evaluate for yourself. If you disagree with what I did, that's fine. You can go look at the data yourself, provide your rationale for why you think it's wrong. It's, again, open communication, open transparency is the goal. So an AOP evaluation, when you look on the AOP page within the wiki, this is one of the last sections that you come to, but it's an important section, particularly, again, for the regulatory use. In the assessment of the overall AOP, we want to define its applicability domain, talk about the support for the essentiality of the key events, the weight of evidence for the key event relationships, our level of quantitative understanding, and then the overall assessment of the confidence in the AOP. That information, as you saw earlier, gets summarized in these various tables. So for each key event, we're making a call about either strong, moderate, or weak for the weight of evidence, strong, moderate, or weak in terms of our quantitative understanding. That gets reflected in that network view, so you can just go in there quickly, see a snapshot. If you see nice big bold arrows, you can say, oh, pretty confident. At least the developer was pretty confident. When you look in the user's handbook for developing AOPs, these different types of evidence are sort of ranked. They're presented in a rank order. This is basically arguing that if you look at the strongest independent evidence to weakest, plausibility is considered the #1 sort of best support you can provide for the AOP. If it makes sense relative to what we know about the biology, that's the greatest sort of confidence that we can get, that this makes sense. Support for essentiality is kind of the second. If we can demonstrate causality in the sense that if we block this event from happening, nothing else downstream of that will occur, that's pretty compelling evidence as well. But that's usually focused on specific key events, doesn't necessarily extend across the whole pathway always, so maybe a little bit weaker there. Empirical support, saying, I've shown this relationship once in a particular species, in a particular study. That's nice, but show me again, particularly if you don't know why that happens. You better show me many times that you can see this and then see this downstream effect every time you do it, if you don't understand how it happens. So in terms of evaluating each of these independently, that's sort of the rank order that's assigned. But again, the ideal case is if you have all of those types of support. If you know the plausibility and you have empirical support and you can show that if I block this, I prevent this, that's the strongest evidence you can have. Okay, so thinking about those in terms of the rank ordering then, what are the defining questions that help us assign strong, moderate, or weak call to that evidence? When we talk about the plausibility, the basic question is there a mechanistic relationship between the key event upstream and the key event downstream that's consistent with our established knowledge the biology, structural or functional relationship. If we have a well-understood pathway that's based on extensive previous documentation, it's well-established, maybe it's just dogma in biology, that thyroid hormone plays a role in amphibian metamorphosis. It's pretty well-established. So if you have that, you can make a strong call for plausibility. A moderate call would be saying we have scientific understanding of this relationship, but it's incomplete. There's a couple uncertainties here. Weak would be it's a previously undocumented relationship, maybe one of these relationships that Steve's done through literature mining and fancy computational techniques. We've got an association here, but something completely new that we've never tried to connect before. It's largely empirical observation, no real understanding of the biological basis. That would be weak plausibility. Essentiality, again, we've talked about this multiple times. It's this consideration, if we block or prevent a key event, do we prevent the downstream? The defining question there is just that. Strong support would be direct evidence from specifically designed experimental studies that illustrate essentiality. This would be things like knockout experiments. So if we say, binding to this particular receptor is critical for this effect to occur. If you knock out that receptor and add the chemical, you shouldn't see the effect, right? Those types of studies, reversibility studies, where you add the stressor, you see the pattern of key events, you remove the stressor, you see the pattern go away in the same order that they were induced in, that's pretty strong support. Moderate support would be where you have indirect evidence that some experimentally induced change in an expected modulating factor attenuates the response. So we know that I can change plasma estradiol levels by changing some external variable. So I modulate that response and I see changes downstream of that. That would be sort of moderate support for essentiality. Weak, I have no or contradictory experimental evidence of essentiality for any of the key events. This is an example of an experimental study that would provide direct support for essentiality. So basically we have an AOP here that links NMDA receptor binding, or antagonism rather, to impaired learning in rodents. So MK801 is a well-known NMDA receptor antagonist. So under typical conditions, if you administer that chemical to a wild-type mouse, you cause reductions in their performance on learning tests. If we use a transgenic mouse that lacks a functional NMDA receptor, expose them to that chemical, compare them to the wild type, and we basically see no effect on the knockout mouse, but we still see the effect in the wild type mouse. That would be evidence that the NMDA receptor is essential for that adverse outcome pathway. Make sense? Another example, again, from the studies we talked about earlier today, exposing fish to an aromatase inhibitor. In this case, focusing on this part of the test where first we expose them to the chemical, we see the effects on the key events, see eventual compensation, but then we remove the stressor and we actually saw those events rebound. So the estradiol production by the ovary bounced right back, and in fact it exceeded the control levels because we had caused that compensatory response, and they'd actually increased the amount of enzyme they were producing, so they produced more estradiol than the controls. We turn off the chemical, and again, plasma estradiol levels do the same thing. They rebound, come back above the controls, and then bounce back down. They do that in the same temporal order that you saw the initial impacts in the first place. So again, provides fairly good support for essentiality. Empirical support for the key event relationships. Our calls on that are really based on, again, these Bradford-Hill considerations, dose response, incidence concordance, temporal concordance. Strong evidence is where we have dependent change in both of those key events for a wide range of specific stressors with few or no data gaps. Everything hangs together. We see it for multiple chemicals under multiple different scenarios. Moderate, we have data with a smaller number of stressors, maybe some explainable inconsistencies in the data. Weak, we have limited or no relevant studies, or we can't explain some of the inconsistencies that are out there in the literature. So that gets us through plausibility and empirical support. What about quantitative understanding? How do we make the calls about that? It's really based on consideration of three key elements. One is the precision with which the downstream key event can be predicted based on the measure of some upstream key event. So if I measure key event upstream, more precisely I can predict what that downstream is, the more quantitative understanding I have. It's also dependent on the degree to which other known modulating factors can be accounted for. So if, for example, temperature or pH affect the shape of that response-response relationship, if I know that, but I have no idea how to account for that, it's a little bit weaker. If I know that, if I have dietary stress, nutritional stress of the organism can change this relationship, but I know exactly how to incorporate that into my model, then I can put it back in that higher category. Then finally, the degree to which the quantitative relationship generalizes across the applicability domain of the AOP. Say I've built a model that accounts for these feedback processes. That gives me a good quantitative prediction of the effect of estradiol on reducing estradiol on vitellogenin concentrations, but I've only validated that in one species. It works well for fathead minnow, but it doesn't really apply to zebrafish or rainbow trout or let alone frogs or birds. That produces weaker quantitative understanding than if I had a model that I could apply to the entire applicability domain of that AOP. That gets us a little bit to talking about domain of application. I won't go into this in great detail, but one of the things you do in the overall assessment of the AOP is trying to define the relevant biological space that it applies to. So again, we kind of talked about that in the first presentation today. What taxa is it actually relevant to? Physiologically, what are these key events? Which taxa actually can make eggs, for example? Life stage, sex, all these things kind of bound the domain. And generally, we define each of these for the key events. So we say this key event, this enzyme is only found in vertebrates. So that would narrow our scope to vertebrates. We say this particular protein, vitellogenin, is only physiologically relevant to females. So now we've confined ourselves to female vertebrates. So basically, the most restrictive of your key events in terms of the taxonomic relevance will generally define the overall applicability of the entire AOP. This is just a table that you'll find in the user's handbook that takes these different factors related to quantitative understanding into account, and sort of, as you address each of those, the precision, the degree to which you can account for modulating factors, and the generalizability of that relationship. If you address each of those in the context of strong, moderate, weak, it'll help you guide you as to what call you should make relative to the quantitative support. Finally, one of the key things relative to this is not just to make the call in the table and say I called it strong, moderate, or weak, but actually provide the rationale. So in the context of these guiding questions, why did you make the call you did? And that's not to say you need to reproduce all the data. All the data that support this are already captured on the key event relationship pages, but you want to give a general impression of, why you made the call you did. Because I had good empirical support, but it was just from a couple of different species. We're not sure, we don't have any data right now that says this could apply to these other species. Something like that, just a general description, but again, gives your rationale in a very transparent manner. Overall, this weight of evidence evaluation and these calls are not trivial to document, but We do think it's critical to the application of the AOPs in the regulatory community. So it's an important thing to do, even though it's not necessarily the most fun, enjoyable thing to do. Effective summation of this expert opinion gives us that expert opinion regarding confidence and extrapolation along the AOP. And again, transparency and rationale are presented for what is inherently a subjective determination. So if somebody wants to challenge it, they're welcome to do so. All the information is there. Everything's on the table. The debate can begin.
Okay. So I'm going to do AOP training and log in. Okay. So I am now a logged in user, which means you can see already on the main page, you see I've all of a sudden gotten these little edit windows. So that's good. That means I can edit things. Now the first step, if you want to create an AOP, so the way the wiki works is we have a basic wiki that functions just like Wikipedia, and then we have another piece of software which kind of tracks all of the connections. And so, and unfortunately right now you have to log into each one separately. So if we want to create a new AOP, I'm going to click on this link, and that's going to take us into kind of this other world. It is the same username, so I would still log in as Breakout 2 with AOP training. It's just you have to, we could not figure out how to get the two to talk to one another. And so that brings up a page where you've got a short title, long title. So we'll say CTAC course aromatase and aromatase inhibition leading to what do we have? Decreasing population trajectory. All right. And so this puts us in what we call the widget page. So again, this is it's putting information into the wiki, but it's doing it in such a way that it kind of connects all the dots that need to be connected. So we can add a molecular initiating event. And I went through earlier. So if an event exists, you can use that event. And so what you really need to do is you need to search around and find, are there events in the wiki that match what you want to use, and kind of get an idea of what those names are. And then if you do that, then if you start typing the name, it's going to show the things that match that name. So what I did is during the earlier talks, I actually went through and found a few of these things. Those calls are not required, and in fact, unless you're putting in the AOP after the fact, we actually encourage that you don't put an essentiality call. The whole premise behind this is by the time you make that call, you have evidence to support it. So it is there when you create the key event, simply because a lot of people have done the whole process before they start entering their information. So then our next one was reduction in estradiol in the granulosa. Any essentiality call on that one? Key event 2? All right. All right, and in the interest of time, I'm going to skip a couple, and I'm going to go to a reduction in egg production. And I did this on purpose. I used their key event, which didn't match. So this just shows you that the same procedure is used regardless. So in this case, what I'm actually going to be doing when I hit submit is this is going to create a new key event in the wiki, which will then be available to other people to use when they start. So again, you have to do a little work up front to figure out what can be reused, and that's the part that hopefully we will get a little better at helping you find these things on the fly. But once you know, it's fairly straightforward to add existing key events or add new key events. And then the adverse outcome was in there already, so I can once I get enough of it, I can add that. And you'll notice that the adverse outcome doesn't have an essentiality call. That's because it's the anchor for the whole thing, right? So if you're not predicting that adverse outcome, you don't have an AOP. So now we've got a handful of key events. So I'm going to connect the dots. So we're going to take our MIE, and we're going to say it directly leads to our first key event. Did you guys make an evidence call on that first relationship? Strong? All right, so we'll go ahead, since they did all the work and have a definitive answer for us, we're going to go ahead and add that in here. All right, and then we're going to add our next one, which is going to be this one. And again, ordinarily we'd have so you have to trust me, there's two in between, which aren't going to show up on this one. So I'm going to make this an indirectly leads to, even though it just hit me. It won't matter because our network diagram's not working on the training wiki, so you won't get to see them anyway. But if you got to see them, you'd see a little nice dotted line. And then we've got our egg production directly leading to our adverse outcome, and we could make a call there. I'll just give it a lower number and pretend that I could actually show you a network. And then you would undergo a similar process below if you wanted to address life stage. So we have a list of terms you choose from. The evidence calls are the same: strong, moderate, weak. And you have one for life stage, one for species, one for sex. The species is a little different. I guess I could show you that in that it will, I don't know if we have fish. It will, let's say this one, right? And then what it will do when you put in your common name is it will search and see if it can find scientific names that match that. And so we try and encourage people to be as precise. Now, you wouldn't have to enter this, but we try to encourage people to be as precise as possible. And like I said, the evidence calls are the same across all of them. And then once you are done with the widget tables, you can go to your newly created web page. So the first thing you can see is that the wiki page already has all the headers that you need. So it's formatted correctly on the front end. And you can see that everything that I put into my widgets were here. And if this were working on the training wiki, you'd see one of those networks like I showed you this morning. And so you have all of this to start from. Just to show you how the text sections work, I'm going to add this. When you get into here, the headings have these little equal signs around them, so you don't want to mess with that. That's what makes them show up on the template. So we're going to say CTAC Working Group 1. And then we'll come down here and click Save Page. And so for all the text fields, that's the way you do it. There's going to be an edit link beside the heading. You click that edit link, it pulls up the box corresponding to that heading, You type in your text. If you know Wikitext, Wiki Markup, and want to use it, you're welcome to. If you have no idea what I just said, that's fine too. So that's pretty much it for how you would use the widget pages. Like I said, the other ones are very straightforward. You have these edit boxes on each page. You do have a handful of widgets on the key event pages. So you can see here, since I reused aromatase, you can see that in addition to ours, we've got several others where this has been used previously. And in fact, we've got, because this is our training wiki, we've got group 2 from a previous class, group 4 from a previous class. Here you guys are. So you can see we have chemical initiators and taxonomic applicability, level of biological organization. So there are a few widgets on the other pages. You would access them the same way. We go to a widget page for each one. It has, the ability to add. So again, each one, the bulk of the widgets correspond to the AOP page. You would notice that I was not able to edit this section on the key event page. This gets automatically populated. So changes on the AOP page would influence this table, but there's no editing here on this one. Comments. So for that, I'm going to go back over here. I'm going to log in, but as I mentioned before, for commenting, you mind if I just log in as you? All right. I'll comment on one of your AOPs. How about that? I was going to say, I'll comment on one of your AOPs so that you'll know. Okay, so what you see now is that, actually, I logged in as Dan, so he could edit anywhere. If you were logged in as a non-author, you would only be able to edit the discussion pages. But what I do want to show you, let's see, find one of his. Well, why don't we do aromatase? And so I'm picking Dan's because I know that he has, that this is undergoing OECD review. So again, you get this tabbed thing. So if you go to if you go to the discussion page for an AOP that is not being reviewed, it's just going to be a blank page. And so you can put your comment on the page, or if there's other comments, you just put your comment down at the bottom. But this one's a little bit different in that we kind of have this second tab. And unfortunately, again, we're using the wiki, good with the bad, bad with the good, whatever you want to call it. So when you get in here, you've got these little equal signs again. Kind of goofy. We have, in the help, we tell you how to deal with this. But since I have you here, I want to show you. So if we wanted to make a comment, so again, we're not part of the formal review process, so we want to leave everything from that point downward. We don't want to touch it. But we do want to say hey to Dan, so we're going to say example comment from CTAC training. I won't be too explicit since this is actually on the real wiki. And then up here, there's this little squiggly sign that looks like you signed your name, and you just click that. And then if we come down here and save the page, what we will see is now it has noted who it was that made the comment and what the comment was. Now, if this were really somebody else commenting on Dan's AOP, then he would come in, click that edit box, go underneath that, put his response, and then click his signature, and it would show that he had responded. So again, making comments is very simple. Making comments does not require any effort beyond creating your own account, verifying that your email, because again, we had some spam bots. But you don't have to ask for anything. No one grants you anything. It's immediate as soon as you confirm the email. And if you have any problems, there is an email address right here on the front page. While I'm happy for you to email me directly, if you email that, it goes to about 3 or 4 of us, and whoever gets it first can deal with it. If you email me, it gets buried in about 100 other emails, and I find it 2 months later and say, oh man, I'm so sorry I didn't get back to you.
Just wanted to touch on 2 other things, well, maybe 3. So first of all, just want to acknowledge some of our colleagues. So we're here doing the training today, but there's actually a larger group that's involved in developing these training materials and giving training sessions to various groups. So they're just listed here. Again, the idea is to try and get these principles out, provide information on how we do the weight of evidence evaluation, and get the community involved in both creating AOPs, understanding how the knowledge is structured, how we're doing the weight of evidence evaluation, so that both on the development side and the user side, people are more informed about what it is we're doing, how the information is structured, what you'll find there, and how it might be useful to you. So hopefully that course accomplished those goals for you today. Final consideration relative to AOP development as well. You know, one of the questions we get is, it seems to be a lot of work, so what's in it for me in terms of career development or whatever? One of the things that's come out of the most recent OECD meeting was, you know, once we go through this process of reviewing these, how do we sort of get credit and publish these so that, you know, it's something you can put on your CV, it's something that somebody could cite. So OECD actually has a journal, and it is a indexed journal. You can find it on NCBI, PubMed, all those search engines. And the plan is that as AOPs go into that AOP development program and go through that formal peer review process, if they're accepted or, you know, they've been reviewed and approved by the reviewers, they will be published in the OECD journal and be treated like a journal publication. It's different from a journal publication. It'll be published basically in that same format you put into the wiki. So that static PDF from the wiki, that's the publication. So people have done some of their AOPs and then tried to adapt it to a journal article, and it doesn't translate real well into kind of a descriptive sort of narrative journal article. And so this is a way that you can, again, get credit for the kinds of contributions that you're making to the AOP wiki. So just something to bear in mind. Just like to thank you all for your attention today. I think you'll be getting some feedback forms from CTAC via email, I believe. So if you get those, please fill them out, provide feedback, or if you want, email me directly. We'd appreciate feedback on the course, what worked well, what didn't. We've been doing these to a number of different audiences and so on, and kind of tweaking things as we go. But you know, if you found some things very helpful and other things not, we'd appreciate any of that kind of feedback you could provide.